Why don't we get started just a couple minutes early? I don't think anybody's going to make it in anyway. Just let me start by saying I love this conference, and I love all of you for being at this conference. There are a lot of people in this room, so I'm really, really happy. We're here today to listen to multi-service reactive streams using Spring Reactor and RSocket, a really, really long name. I really have to work on naming. I'm really, really bad at it. For those of you who don't know me, haven't seen any of my talks so far this week, my name is Ben Hale. I'm the lead of Java on Cloud Foundry, which seems like a really odd thing since I'm up here talking to you about reactive programming in Java. And here, my day job is to run a cloud platform, actually. So why am I here? Right? Why do I have this interest clearly from the keynote and all of this stuff reactive? And the key thing is my position running on Java on Cloud Foundry puts me in a position where I see a lot of customers and a lot of customer needs. And when it came time to start talking about R2DBC, I saw how people were trying to connect to databases, and this is a very, very similar thing. We see all of our customers coming to reactive programming eventually. It's a slow trickle now, but more and more we see that this idea of high efficiency applications is really, really key to all of our developers, right? In the long term, no one wants to pay Pivotal as much as they're currently paying Pivotal. No one wants to pay Amazon or Google what they have to pay. What we need to do is get away from a lot of the things that we've done so far when we were just running in our data center and computers were just sunk costs, and so it didn't really have to matter very much. So we want to go to reactive programming, and just a quick review for anybody who hasn't seen me twice before. Fundamentally non-blocking, paired with asynchronous behaviors, but absolutely not a requirement for asynchronous behaviors, right? Reactive generally has no opinion on asynchronicity. The highest efficiency stuff, if you take a look inside a Project Reactor, the fastest stuff you'll see running is Reactor internally doing a thing called fusion, where they take a lot of your operations and they pull them out and glue them right next to one another, running exactly in the same thread, one after another, directly connected, because that is actually the fastest way to run reactive code. However, when you want to do asynchronous kinds of behaviors, reactive really, really works well. The programming model makes asynchronous kinds of things, you might even say possible, right? Key differentiator, we're going to say from asynchronous programming, is this idea of pull-push backpressure, this idea that a publisher can't send me any data unless I have first asked that publisher to send me data. So we see this slide that we saw at the keynote the other day. Composite Health gives us the ability, so reactive programming gives us the ability to now say, I want this thing and this thing to run in parallel with one another, right? These two things don't depend on one another. They can happen at the same time. They can happen sequentially if you think that's a better way to do it, Reactor. But what I want you to do is go get me a URI, go get me another URI, and then once those two things have happened in parallel, sequentially build me a composite out of that. And this really is the key that reactive frameworks are giving you. This is the way they enable this high efficiency, because now you're declaratively basically saying parallel and then sequential, right? You never have to manage the threading or the optimizations behind the scenes to do that. But there are still roadblocks to using Reactive Everywhere. As I said, I am personally a Reactive Everywhere person. That is not the official policy of Pivotal. It's not the official policy of the Spring team. Use Reactive when you think it's right. There are a bunch of places where it's totally obvious. This is where you want to use Reactor. And there are a bunch of places where it's not, and it may not actually pay off. So when we say using Reactive Everywhere that it's appropriate. Data access. The data access side has really been on top of Reactive. MongoDB, Cassandra, Couchbase, Redis, those kinds of things, these NoSQL data sources, really jumped on it. They were created in a time where this asynchronous programming model, especially driven by Node.js, was really common, and so they brought it over. We've obviously started R2DBC as well because we know that relational databases are where all of your data really is, not these guys here. So we want to make sure that that's available at the same time. And then finally, we want to talk about cross-process backpressure, which is a really complicated way of saying, how exactly do I get reactive programming across the network, right? I know that I can say, okay, a publisher inside of my JVM can't send me any more data than I've asked for it, but now I got to go do an HTTP call to another microservice, which is about to send me 10 million rows of JSON, right? Now I'm hosed. And so I'm happy to not announce a project so much as point to a project called RSocket. Historically, RSocket was designed by the team inside of Netflix called the Edge Server Routing Team, I believe is what they were called. These are the people who brought you Netflix OSS previously. They sat down and said, okay, Netflix OSS is great, lots of people out there using Hystrix, lots of people out there using Eureka, things like that, but we think we can do better, right? Before we were sort of hamstrung, internally we knew we had to use HTTP or we had to use TCP, but what if that actually wasn't a requirement? What if we were really, really ambitious and said all of the things that we want to do with HTTP, all of the things we want to do with all of this high availability stuff like the circuit breaker pattern or service registries, load balancing in complicated ways. What if we were more ambitious and we said there's a network protocol that does that, move way down the stack underneath all of these application servers running and coordinating with one another? And so they came up with this great thing, right? RSocket is a bidirectional multiplexed message-based binary protocol based on reactive streams backpressure. There's a lot of words in that. We're going to take a look at every single one of those words in the next couple slides. And it provides out-of-box support for the most common interaction models, especially once you take channel into account. You realize it's a bailout and you can do any kind of interaction model with it. So what is a message-driven binary protocol mean, right? So if you think about how HTTP is supposed to work, you make a request and you get a response back. Much of that request, so you get a document back, effectively. You call that a document-based protocol. A single request returns you a document of some kind, whether it's HTML or it's, JSON or something like that. When we talk about a message-driven binary protocol, what we're talking about is all of the requester-responder interaction is broken down into a set of frames, something very small, that encapsulate individual messages within inside of them, rather than a single blob of text going out and a single blob of something else coming back. We get these discrete frames saying, this is a request. So I can send a bunch of requests independently of one another to you, because this is a message that says, I want you to go get me something. And when it's time for you to respond, you don't just sort of give me a fire hose of bits. You package them in little messages that are going to come back to me. The framing is binary, which is really counterintuitive, especially coming from, 20, 30 years now of HTTP, right? It's so common for us to fire up Wireshark or something like that, some other proxying mechanism, and just look at the headers that are going by, right? Everybody knows what an HTTP request looks like in ASCII text. But what we find out is if you choose binary instead, it is incredibly smaller. It has much better compression. We have massive efficiencies for machine-to-machine communication. And by the time we're talking about RSocket and the scale that sort of RSocket wants you to work at, this is a huge, huge improvement over something like HTTP. The overhead of the protocol itself shrinks so much compared to the data that's being transferred in it. Downsides manifest rarely, primarily when you're trying to figure out why the hell doesn't this work, especially for people who work on RSocket Java or RSocket Go or RSocket Kotlin or something like that. The stacks, the libraries that actually implement this protocol, trying to debug this can sometimes be a giant pain. But there's enough tooling in the world around. You can write Wireshark plugins, for example, that know how to decode the binary data as it goes by, and we can take a look at that. The one key thing, we've been talking about, sort of the binary nature of this protocol, is that the payloads themselves are the exception to this idea. Payloads are just bags of bytes, right? The protocol doesn't actually tell you what a payload needs to be. It doesn't need to be ASCII text. It doesn't need to be JSON. It doesn't need to be protobuf, to name another protocol, gRPC, that advertises very similar kinds of things to this. So it could be JSON. It could be XML if you're still XML kind of people, because internally the protocol says it's just a bunch of ones and zeros. We're going to give it to the client, or we're going to give it to the responder or the requester at the end, and they're going to decode it the way that they want to. The protocol itself is also multiplexed, and this, when I first got started with RSocket, was the most amazing epiphany I had about networking, right? So what does this mean? Connections that only used a single request are massively inefficient. We saw this in HTTP 1.0, and so HTTP 1.1 came out, and they said, okay, you've got a connection, why don't you just send a bunch of requests, and the order that you send them is the order you expect to get responses back from them. Well, trying to manage that yourself was always giant pain. Most web frameworks would take care of this for you, but there were still issues. right? What happens if I send 5 requests over this single connection to you, but the first one is really slow when the later 4 could have been really fast? And this is why, if you take a look at how a web browser works, it doesn't open a connection for everyone, really inefficient. For everything it needs to go get off of your server, doesn't open one for each of those because lots of connections are inefficient, but it also doesn't open only one, because now all of a sudden slow requests can interfere with fast requests, and more or less you're stuck in a situation where your web page is likely to render only as fast as the slowest possible thing, no incremental loading. So this is really, really bad, even in HTTP 1.1. Multiplexing solves this issue. It opens a single connection, right, a single physical socket, or I guess it depends on what you think physical means, physical socket between 2 servers, and then it says, okay, within this pipe, I'm going to send one message that says, I'm stream 1, and then it's going to send another message that says, I'm stream 3. And those can return in any order that they want. If 1 is slow and 3 is fast, that's okay that 3 can come back. Because rather than saying, the way I know what you are responding to is because you are coming back first and then you are coming back second, you've actually tagged both the request outbound and the response inbound. And it says, hey, 3 is coming back now, go do whatever you need to do with 3. 1 comes back a little bit later and says, hey, go do what you need to do there. And this is really great. This has really influenced a lot of my thinking, especially around R2DBC. So we've asked the database drivers, say, hey, you know how everybody can only get 4 connections to your database or 8 connections to your database? Why don't you have them have 1 connection to your database, and then they can have a million streams across it, as much sort of logical behavior as they want to on those things. And for example, the Postgres team is starting to look into this idea. This, as far as scalability goes, is one of the most amazing things you'll ever see that came out, or that is sort of integral to OurSocket here. The protocol is also bidirectional. This has some really interesting use cases. So many protocols, specifically not TCP, have the distinction between a client and a server for the lifetime of a connection. So if you're HTTP client, right, like a web browser, you can make a request to a server, HTTP server, and it may respond to you. And that's it, right? That's the only way data can ever be transmitted, right? One side initiates all requests, one side initiates all responses. Even something like HTTP2, which nominally is supposed to be, it is, for example, multiplex, so yay there. Even something like HTTP2 doesn't fully drop that distinction, right? There is sort of a mechanism for data to be sent from the server to the client, or data a bit, but servers can't start an unrequested stream. Clients basically have to say, okay, I'm ready to listen for you to start sending me some stuff. So they've effectively initiated, half initiated an interaction there. So what we say with RSocket is that once a client initiates a connection to a server, right, so in our analogy, web browser connects out to our server, both partners, we basically lose the distinction. There was a discussion in the company Slack the other day where we were trying to explain this to some people. It's a really hard concept to grok. Server and client disappear. Both peers are now equivalent to one another within this network connection. Either side can initiate a request to the other side. Either side can initiate a response. Both of them are really equivalent. And this has a really interesting side effect when it comes to security specifically. Imagine a router sitting in the middle of a bunch of different clients all inside of containers. Today, my work on Cloud Foundry tells me that the biggest possibility of compromise of a container in a cloud environment is you've got an HTTP port coming in, somebody gets onto that port and exploits something inside of your container. Now, what if you could say instead that your container had no ingress ports at all? There was no way into it. Only outbound connections could be made. RSocket enables this kind of pattern where all RSockets connect out to some trusted party. But once they're in there, any sort of startup, anybody can request, anybody can respond in any network configuration that you want from there. And it gives you actually this really interesting security posture because of it. I think the final set of words that were on there was Reactive Streams backpressure. Network protocols, HTTP, we're just going to keep banging on it this entire time. Generally send a single request. As I said, we all know what this looks like. Return some sort of arbitrary 10 million lines of JSON back to us. There's nothing to stop a responder or even potentially the requester from going nuts on the server, right? Some huge amount of data. You are protected a bit by TCP backpressure. This idea that the TCP stacks to drop way, way down, like level 2 kind of stack, right? Has these idea of queues, right? Until there's, a SYN-ACK pairing kind of thing as data is sent all the way at that low TCP level, more data isn't going to be sent. You can't blow up the network stack of a modern computer. But what ends up happening is you end up with huge queues of unprocessed data or untransferred data. Both on the client receiving side, you'll get a bunch of data sitting in a TCP queue that hasn't made it back up to the application. And over on the sending side, you're going to end up with a bunch of queues that haven't been able to get across the wire yet. And this is really problematic simply because if you have a lot of connections with a lot of full queues, it requires a whole lot of memory, and this is really bad. So Reactive Streams backpressure here ensures that we only materialize data and transfer that data when the receiver is ready to process it. The receiver literally sends one of those messages, one of those frames across the wire and says, okay, you're now allowed to send me the next 128 messages. You're now allowed to send me the next 64 messages. And that's a signal to the server side that it can go to a database and read those off disk, or go to another microservice and go grab some more data, materialize it, and send it along. Don't materialize it before I can handle it, and that is actually good for you as well, you for the server. So let's take a look at interaction models. The first interaction model, we said there are 4 of these, right? The first interaction model that we always talk about is request response. The idea of I want to request an account number, I'm a banking app. Sorry, let's go with that. I'm a banking app, right? And I'm looking at it, and the first thing I do is I log in, and it's going to show me a splash screen, and so it knows my account number. It makes a request out and says, hey, go find me exactly what the balance is for this particular account number. Standard request response semantics, we see the line all the way up there at the top, so it's a mistake given how short I am. Client request response, you pass in a request payload, just a single object, right? Whatever it is, let's call it the account number in this particular case, and you get one of these mono payloads back, right? For those who've missed it in some of my other talks, all of this stuff, anytime you're going to see me do a demo up here, RSocket especially, is based on Project Reactor, which is sort of the Spring-affiliated implementation of reactive programming. There are other alternatives, there are other languages, but fundamentally we have 2 main types in Project Reactor. We have the idea of a flux, which is a stream of 0 to n things that will come back to us, element, 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 and a mono, which means either 0 or 1 of these things are going to come back to us. So in this case, we say, we're going to send you a response. We expect 1 payload to come back. Now, this is almost certainly exactly what you do. We have been so brainwashed into doing request response from HTTP, and realistically, most of the information we want to know is a request response kind of interaction. So nothing wrong with this, but even this, something that you know you can do today in HTTP, it surpasses HTTP because it's asynchronous and multiplexed. We need a single connection where I can just send a million request response calls and get them all back in a jumbled order as fast as they can be processed on the other side, something you cannot do today with HTTP. The next one is sort of an optimization of request response. We call this fire and forget, which is a very, it's a very American thing to say, certainly. I'm not sure if it has a great translation on the other side, what with our gun culture. This time we see a mono void, right? And a mono void is sort of a special idiom in the reactive world. And this basically says, hey, I'm not actually waiting for a response. You're always going to send to me 0 because void is not a type that you can instantiate in Java. So all I want you to do is signal to me as soon as you're done. So when we say fire and forget, we want to send you a payload, and I don't care, right? Like, it's going to get there. The TCP stack will guarantee the payload got there, but you don't need to tell me you got it. You don't need to tell me you're done. It's just going to go over the wire, and I'm going to go on with my life. There are significant efficiencies for this, mostly on the networking thing. Imagine a scenario where I sent you, what do I have here? Non-critical event logging, right? I'm going to send you a log line, and maybe you need to sync that log line into a database. Well, realistically, that's going to, to take into a database, you're going to have to wait on the connection pool to get it, going to have to wait for the insert and the commit that follows it after the database. writing to the disk. It may be half a second before you can get back to me and say, hey, this was all done. But if I don't care, right, if event logging isn't particularly critical, then why don't I just say, hey, here's a piece of data and you can release it immediately. You'll go on with your life, you'll still try and get a database connection, you'll still try and sync it, disks will still write, but you've released a network connection or a logical connection from your side. I can go on with my life without having to wait around for you to come back and tell me that you're done. On the, for sort of less trivial kind of stuff, client-server processing, the key thing here is to make sure that we're releasing these kinds of resources as quickly as we can, especially in sort of non-blocking, high-efficiency kind of environments. So the next interaction model is request stream. The example we have here is, again, request with an account number, and I want you to then give me a real-time stream of all of my account transactions. Literally not the ones that have already happened, but as I'm standing here, and my brother's over there, and he's got a credit card, and he goes and swipes it to get a coffee or something like that, it can show up in my app, right? This happens in quite a number of sort of modern, especially credit card apps really like to do this kind of thing. What we end up seeing here is when we go and call request stream with that same payload, this time we don't get a mono back, we get a flux back instead. We are going to get a stream of these events. And maybe the first thing that shows up is all of the transactions that have happened over the last hour, the last 2 hours. But we don't signal that this stream is complete, right? That's just the first bit of it. It gets written on my app. And now, every once in a while, another thing comes across us. We're still listening, just waiting for it, and that gets written in, right? So it's analogous to a request response where it returns a collection, except each element comes in alone because it's effectively a never-ending collection. One of the key things here, this is the first interaction model that we're taking a look at where request end semantics, which is what we call sort of reactive backpressure. And the reason we call it that is the way this works is you do a subscription, so you basically say, hey, publisher, we're all ready to go? Yep, everything's ready? Okay, request 4, request 8, request n, effectively, and that's how we signal to the publisher to send me data. So the key thing here, once again, is suppose that very first thing, we say, okay, go get me the first 128, but there's actually 10,000 things that have happened in the last hour, right? It can't send me that 10,000. It's not materialized, not ready to send. All of a sudden, I start seeing a ton of data coming in on my phone. I'm like, oh no, cancel, right? Maybe it only got halfway through that 10,000 that it needed to materialize. It didn't have to spin the disks underneath the database to get all of that data up. So there are huge performance improvements that you see from this. And this is one of the really interesting things. The original author of this particular protocol, or one of the original authors, I should say, eventually went to work and took this with him at Facebook. And the key thing that they were looking for at Facebook was that kind of efficiency. We're going to talk about a ton of other, sort of improvements that you're going to see on this as the talk goes on. But they really were interested in this idea that they don't have to materialize a bunch of data that will never get to customers. At, sort of at the scale of something like Facebook, this has material dollar values. Think of, how many applications, how many phone apps are currently running and connected to Facebook at any given time. So it actually makes a really, really significant difference. So the final interaction model that we're going to take a look at here is channel. The example I have here is incredibly contrived. Like I must have spent 10 minutes trying to figure out something it is. Request something with an account number, you're going to respond with that real-time stream of account transactions, but then I press a filter button, and that filter button says, I only want you to show me the ones that are for coffee. And so then it goes and enumerates a whole different list, and then my brother next to me right here goes and buys a coffee, and that is the only thing that shows up, right? Really contrived. I am sure there are no apps that actually do this. But the key thing here is, while we see the Flux payload coming out, we'd expect that, sort of a stream of data, but we also have a Flux payload going in, and those could be two different kinds of payloads. They don't have to be symmetric. And what this basically is I want you to open a pipe, and I'm just going to send some messages sometimes, and you're just going to send some messages sometimes, and you can do anything you want. And if you really think about it, the unstructured channel allows any arbitrary interaction model. Like if you don't like the other 3 interaction models plus this one, you can implement anything that you want. I get to send 1 and you only get to send 2. I get to send 2, you only get to send 1. Doesn't matter realistically. But the key is that if you can sort of think of this as the bailout, you can actually implement all of the other interaction models on top of the channel manually if you wanted to. but we sort of promote those to be, the other three to be first-class kinds of things. Okay, so that's a lot of stuff. How's everybody doing? Okay, so let's take a look at some code. You'll be really happy to know that later bits of this demo were done right around 10 minutes before this started. I was over with the boot team taking a look at the very newest stuff, actually, that they've put into place. So what does RSocket actually look like? Nope, this is the wrong one. Ooh, that's not a great sign, actually. Oh, no. OK, I got it. I know where I am now. OK, so RSocket itself starts, the key thing that you end up with is this idea of an RSocket factory. An RSocket factory is used then to create either a server or a client. One of the key principles of the RSocket API is that it is perfectly symmetrical. Okay? There is this thing called an RSocket. No, RSocket. See if I can do it like that. RSocket has request response, fire and forget, request channel, request stream on it. Now think of this if you were an implementer. The key takeaway from this is that if I'm a server, I need to implement all of those methods. Something around me will call into those, and I will honor them and respond them out. But with a perfect symmetry, it means that if I'm a client, something that has implemented this gets to be handed to me, and I call one of those methods and get the response back from whatever that is. This means that you can do an implementation. One of the, we'll talk about network transports in a second. One of the network transports is simply there is a single object, and you talk one method to another method, and it just goes through this interface. You don't really know what happens. But this gives us this great ability to sort of have a symmetry and an ease of understanding and ease of implementation between these things. Okay. So in this particular case, we're going to set up a server by receiving. We're going to put an RSocket implementation into it, and we're going to say that we're going to use WebSocket as a transport. We'll talk about that a little bit later on. And we start this guy up. And what ends up happening is that at some point, someone will make a call, passing in a payload. We're down at a really low level. We deal a lot with byte buffers at this particular juncture. And this payload's going to have a number inside of it. So we're going to parse out the number that was in it. We'll go ahead and say, hey, we received this number right here. And then we're going to generate a bunch of responses in the other direction, right? In this particular case, because we're doing a request stream, one in, n out. And so in this case, we're going to say, OK, if you send me 1, I'm going to give you from 0 to 1. If you send me 2, I'm going to give you 0, 1, 2. If you send me 10, I'm going to give you 0, 1, 3. And we're going to send all of that data back out to you, and we just simply map it back into string.valueof. So what does the client look like? Well, we see that symmetry in action again. RSocket client factory. We're going to go ahead and connect. This time, we're going to make an outbound connection over the web client transport. And in this particular case, we're going to say, OK, I want to send out, my requests are going to go out between 0 and 10. We'll create one of those payloads here, and we're going to call RSocket request stream. Right? Now imagine then that symmetry. RSocket request stream passing in my message is quite a lot like calling RSocket request stream right here. Right? We just have the other half of that symmetric interaction. And then once it sends us out a bunch of data, right, we did this flat mappy thing here, which basically says, OK, request stream is going to hand me a stream of data coming back. When I send 1, it's going to send me 0 and 1. When I send 2, it's going to send me 0, 1, 2, and then 0, 1, 3, all the way up to 10 in theory. And we'll wait for that to finish. So let's go ahead and start the server. Oh no. Yep. Okay. I think that's running. Been doing so well on demos. It's only a matter of time till it fails on me here. So what do we see here? We managed to send out a whole bunch of data. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, there's only a single connection at 80, 81. All of these things got to go out. But now all of a sudden I see a bunch of processing coming in and all sorts of random ordering, especially when we start getting down here and how often these come back. There is no guarantee of order. We see the server side of this receiving a bunch of stuff. It received 2 different things before it started sending things back out. So ordering doesn't actually matter, right? Effectively, every single time, raw server, we'll go to here. Every single time a new request comes here, we re-execute this in a completely non-blocking manner. If we did sort of a thread sleep for some random period of time, that'd be okay. All of these are sort of in flight simultaneously. And it's all around this idea of request stream. If I wanted to do one of the request responses, you can instead say, hey, request response. I'm going to implement that in some way where I get a payload and I return a mono payload back. I do some sort of transformation. Maybe I go to a database and do some kind of query, something like that. Okay. So let's talk a little bit more about interesting things beyond just the programming model of RSocket. RSocket, it turns out, and this is the thing I think that really attracted me to the project and said, okay, I want to actually become a committer on this particular thing. I want to be there and be a proponent of this, is that RSocket is crazily one of the most flexible protocols around. It's completely language agnostic, right? It's defined in terms of binary frames transferred over a network, which means that we already have implementations in Java and C++ are probably the most mature. Java specifically because of Netflix and the association with the Spring Team. C++ happens to be the language du jour for Facebook. Boy. JavaScript because everybody wants to do this inside of a web browser, Kotlin, Go, and there are many, many more. So in addition to being language agnostic, it's also payload agnostic. We're going to see some sending of protobufs. I personally would always send JSON, but if you're more into CBOR or some custom binary kind of protocol because you're pushing down towards efficiency as much as you can, sure, send any payload you want. It's not like something like gRPC, which more or less is you must send protobufs and nothing else. And then finally, it's transport agnostic as well. This turns out to be really, really key because it allows you to go over TCP where you can. So typically inside of a data center, going over TCP without the overhead of the framing of something like WebSockets or HTTP is probably the most efficient way you'll actually be able to transfer data across a network. WebSockets, though, exist for situations where you don't have that. Say, your phone over the open internet to whatever your edge server is in the cloud. You can use HTTP2, which gets a little bit more efficient because we can sort of piggyback on the multiplexing of HTTP2. And if you are insane and in the finance industry, those two things go together quite a lot, you can use the Aeron protocol, which is this ultra high speed UDP guaranteed delivery with symmetric blah, 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 I don't know. It's apparently the fastest possible thing, but given that TCP, we regularly see like 60,000 requests per second over it, this seems really like a lot of overkill, right? But if we say that it's flexible, how flexible is it? I don't want to do this. How flexible is it? What if I told you that switching from WebSocket, which we said isn't the most efficient way to transfer data, we said, yeah, okay, I just want to use TCP instead. There's this pluggable layer underneath because the frame is all about a binary encapsulated message that needs to be sent from point A to point B. The fact that it's sent over TCP doesn't matter to any bit of the network stack after that. Yep, thank you. Do the same thing on the other side. And we see one little one down there, received 8. Data has been sent. Didn't affect almost anything. Certainly didn't affect any of our program, right? Any of our actual application code. Barely even affected the configuration here. And we could have put in HTTP2, we could have put in Aeron. Really, really easy to get portability. But one of the really key things is it's quite likely if you really adopt RSocket, it's in a heterogeneous environment. You're likely internally server to server within a data center to use TCP. Externally between devices and your edge server, you're going to use something like WebSockets or H2. But you never have to learn a new programming model. It's simply a configuration choice that you have to make. That's a really, really important bit of flexibility. Again, to poke at that other protocol, H2 or bust, right? So safe harbor statement basically says everything I'm about to show you could be a lie. We don't know yet. Some other kinds of flexibility for RSocket. It's programming model agnostic, right? The RSocket interface is serviceable programming model, but not great. It's designed to be a building block. Starting to hear a theme in my talks, right? R2DBC, designed to be a building block. It's not a humane API. People don't use this, right? This RSocket interface is a very, very similar way. You can use it, like the code wasn't the worst code I've ever seen, but realistically, you as an upper level, high abstraction application developer want something different. Maybe you want RPC, maybe you want messaging style. So let's take a look at some other opportunities there. So I said, boo hiss on gRPC, but I get it. Like, I get RPC. I am actually old enough. I remember the last time RPC failed, like in the late 90s, early 2000s, because of all the tight coupling. But this is the industry we're in. We get to do it again. We get to fail at it again. It's going to be amazing. So you're the kind of person who really likes RPC interaction models, and you really like making sure that all your clients and all your servers are absolutely always locked in sync with zero compatibility problems. Yep, great. Probably also people who use mono repos. I don't get it. Let's define a service, right? A simple service. Request a stream of values, request another stream of values. We define what the message request comes in, what the message response goes back out. This is sort of straightforward IDL style configuration. This we compile down into a protobuf. We inject some RSocket RPC goodness that sits behind it so that on your server, you have one of these simple service things, which actually is not the worst protobuf code I've ever seen. But it has our two methods, request of another stream of values, request of a stream of values, takes in a simple request and some payloads, simple request and some payloads from there. Which means then that we can simply implement this, right? Here's that request stream of values that is sort of an RPC style, really highly contextualized, very semantically understandable kind of API, returns a flux of simple responses, takes in a simple request. In this case, we're going to do the exact same thing. We're going to go to the request message, pull out whatever the number was from it, return a range of these things because we are going to return a range of those responses. Let's go ahead and start this one up. I think I made sure from now on we're always using TCP as well. But even with this RPC style, we could just as easily go through, change this to WebSocket or some alternative that you see there. Shut you down. On the client side, this is great. Somewhere in the world, there is one of these simple service clients. Let's take a look at what this thing does. It's got a bit more code in it this time. But it looks very, very symmetrical. Here's request another stream of values, takes in a simple request and a byte buff. Here's request, or instead of request another, here's request, simple request and byte buff. And so I can build all of those things with this sort of direct, very direct programming model. I should just start using command O. Okay, so I create a new one of these clients, passing in that RSocket client that I created, and that gives me the ability to create myself a new simple request and set what its message is going to be, and then make the request a stream of values, or request another stream of values if I wanted to go that way instead. Get nice auto completion. This looks like calling any other method. The fact that it is going over the network is invisible to you. So output, once again, does pretty much exactly what we want it to. This is a step above the RSocket interface, right? This is a really good strategy. I think we can all agree using the RSocket interface isn't good, even if we disagree on RPC. So how about a third kind, all right? If you're familiar with Spring, don't look at that countdown latch there. This was the bit that we were working on right at the end. If you're familiar with Spring, one of the things that we've always been really, really good at is this idea of allowing you to just write a method that has some inputs, that has some outputs. You can basically choose any damn thing you want and whack in an annotation on it, saying, hey, here's what I want you to do, right? Whether this is HTTP control, or sorry, WebMVC controllers or WebFlux controllers or something like that. It gives you a really loose coupling from the things that are going to call you. You don't know how it's going to get there, but somebody's going to somehow say, I want to send, or I want to call a request stream. I'm going to pass you a payload. I want you to return me a flux. Once again, we do the exact same things that we've always done there. With our flux range on the way back out. You'll notice one of the big deals is that we're not using payload this time. Spring is really good about auto type coercion as well. So something is going to convert into a string for us here. We'll go ahead and return a string out. It'll turn it down into those byte buffs that need to be sent back across the other side. Configuration in this particular case is great. I'm using Spring Boot 2.2 M3, and I did nothing. No, that's not true. I lied about that. On the server side, I had to do application properties. I had to say that we're going to listen on 8083 for the Spring stuff. Nope, that was not at all what I wanted to do. Spring server. We did a little bit of customization just so it knows how to encode and decode strings by default up until about 30 minutes ago, when a change was committed to Spring Boot, it only does CBOR and JSON, but now it'll do it'll do strings as well. But easy customization using sort of standard Spring Boot kind of ways of doing customization here. We'll go ahead and fire this particular thing off. And so now all of a sudden we have a server that doesn't implement an interface directly, so it can be a bit more flexible. All it knows is someone's asking me to route to request stream. It wants to send me a string-based payload. I want to send a bunch of string-based payloads back in the other direction. We see that the Netty RSocket server is now running on 8083, Spring client. What does it look like to go in the other direction? This isn't actually really a Spring app, but we have this sort of utility called an RSocket requester. It wraps the RSocket client-side behavior. This is, again, me setting up some configuration that hopefully you won't need by the time sort of M4 RC1 comes out. But here, we get to do this thing where we get to say, hey requester, go route me a message, to request stream, that endpoint that I saw on the other side. I want you to send this data, and I want you to go return me a flux of strings from that. This basically translates, when you say retrieve flux, is effectively it's saying, hey, execute request stream for me. Give me a bunch of data back, automatically type coerce it into a string, and I'll fire some more data off. I ran this once, so hey-ho. There we go. And it all comes back. So there are multiple ways, because RSocket is so flexible, it sort of sits in this sandwich between a bunch of protocols it doesn't, a bunch of network transports it doesn't care about, and a bunch of programming models and payloads it doesn't care about sitting on top of it. It makes it really, really flexible. So you've seen those three, raw RSocket, RPC style, messaging style. We are actually interested. I am down on RPC, clearly. But I know that the industry has a huge preference for it. And so we're really interested in hearing what you like to do. Should we focus more energy into making RPC better? Should we focus more energy into the messaging style? Is there some other kind of programming model that you'd like to see that we haven't demonstrated here? Talk to the Spring team, talk to the Boot team, talk to the RSocket team. We are really interested in how exactly you're going to use something like this. So we're going to spend much of the rest of this time talking about other features that are in the RSocket protocol, because clearly sending data back and forth, this is what we're here for. But as I said before, when that Netflix team sat down and said, we want to do this better, they didn't stop with, I want to transfer data better. What they actually sat down to do is they said, I want to make distributed communication better, right? They didn't just stop by saying, hey, I just need request response or these 4 things and some frames to go back and forth. What can we do in a protocol that allows us to remove a bunch of the overhead that we see with other distributed systems? So one of the first things they did was that every single frame that gets transferred back and forth, every single frame, most frames, has an optional metadata payload associated with it. And so you do have to sort of define up front, hey, I'm going to send metadata, and the metadata is going to be of this MIME type, so it's totally unstructured. You get to pick. Do you want to send a bunch of JSON along? Do you want to just send a string along? Do you want to send CSV along, like as the metadata? Gives you enough information so that you can decode what the metadata says and be on with your life. right? So it's super flexible and generally is used to carry metadata about what's in the data payload. So this means now that across a single connection, you can actually send heterogeneous types of data. Imagine a company that needs to send a bunch of social media to your phone. Some of it might be text, some of it might be images, some of it might be video, all over the same connection, because every single payload that comes across, they have the ability to take a look at the metadata associated with this frame and say, hey, what should I decode this as? Wait a minute, 41. We also have this idea of fragmentation, payload grams, so that must have said frames. This was very late last night. Payload frames have no maximum size. This is a protocol that came from a company that's responsible for, what is it, the vast majority, over 50%, I think, of all traffic on the internet. They really like sending you really big, high-quality videos, right? So it's really great for serving those kinds of payloads. But the reality of the situation is, if I had to send you a frame that had your entire 4 gig, high-def HD, 4K HDR video of the latest Avengers movie or something in it, you're going to die, right? Your network connection can't handle that, something like that, both TCP, MTUs, and just general reliability. So it has this idea of fragmentation, but it's handled transparently. You can say, hey, I know that, I probably, even though I need to send you 4 gigs, I probably only want to send it to you 1 meg at a time. If 1 meg fails, we can go retry it, have another crack at it. I don't want to wait for us to get to like 3.99 gigs and then have to start that whole thing over again. But the key thing is it's placed into the stream in such a way that it's completely transparent. Software developers, people sitting up and saying, request response, go get me Avengers movie, stream back Avengers movie, never realize that this fragmentation happens under the hood. It allows you to continue reasoning logically about request end semantics, about how, I asked for a single payload and I get a single payload, but the protocol does allow you to optimize for network conditions you are currently in. There's also the idea of cancellation, and this is something that almost no other protocols have, and turns out to be, as we said a little bit earlier, really, really interesting. Because cancellation is a signal by the requester to say, hey, I asked you for some stuff, and that might have been really expensive for you to build, so just go ahead and stop doing that. Right? Request stream and channels, obviously, but even in something like request response, where I'm going to do a request, and maybe you're going to, you have to go do something expensive and come back with a single result, like, I don't know, go calculate my current credit rating or something like that, where I'm going to get a single response, but maybe I have switched off and I've gone on to a completely different bit of my banking application. So why don't you just go stop that? Server side, you can reclaim all the CPU usage you were about to do and give it to some other customer. There's the idea of leasing as well. So leasing is a way for servers to communicate load back to clients. So we said that with request end semantics, a requester can say, okay, we've got a connection, send me 8, send me 10, and I'm not going to send you another request for one of those until I'm ready to go. But what's to stop me as the requester from absolutely spamming the server at the other end, saying, okay, I need request, all the way like that, right? You could totally take down a server. And so the protocol has built into it the way that the server can basically tell any client that's currently connected to it, it can say, hey, you're allowed to send me 10 requests over the next minute, or you're allowed to send me 10 requests over the next hour. And it's totally dynamic. So you can imagine a scenario where the server side is sending these leasing notifications based on the current load. If you were the only person around because, it's the middle of the night, it's a European bank, and 1 or 2 people are there, maybe they get unlimited, right? You get to do int.max level requests over long.max time, right? But then as people come up in the morning, new leasing messages are sent out to say, okay, well now my CPU is up at 50%, so now you don't get to ask me that many times. And this really triggers client-side load balancing really well, because you can imagine an algorithm there where I know I can connect to a bunch of different servers in my data center, and one of them is telling me it's totally full, no more load, nope, don't want to hear from you at all. And so that causes me to flip over to the next client, and that's got leases still, so I can go out and make a call to that particular one instead, open that connection, make those requests. Okay. And finally, I'm pretty sure this is the finally, resumability. Resumability is really, really interesting and comes about absolutely out of sort of the social media cases. Imagine a scenario I have a phone, I've got a news feed going on my phone, and I'm on Wi-Fi because I'm in here, and I walk outside. Immediately my Wi-Fi drops, and I go onto the cellular network, right? So now it's done that. From the perspective of the server at the other side, my connection has died, which means I need to go back, I need to subscribe for all new changes, and enumerate everything that's happened in the last hour or something like that so I can refresh and refill my feed. And you can imagine trying to do that at global scale, at a social network, is really, really difficult. But now imagine it in your use cases as well. Like, clearly this is the really obvious, horrible thing, but you can think of the same kind of thing, where if you have people with intermittent connections, having to re-enumerate so that you can get back into sync where you actually were is really problematic. Inefficiencies both in the network, right? We have to send all of that, everything that happened in the last 2 hours again, and in the data center compute, right? This is where we end up with a situation where we're just running servers, creating a bunch of data that the client probably already has. So built into the protocol, totally transparent to the user, is this idea that both parties, when they come back up, instead of saying, okay, I'm creating a new connection, you can instead say, hey, I'm creating, or I want to resume the connection I just had, okay? Great, so you want to resume? Tell me the last thing you saw, I'll tell you the last thing I saw, we'll synchronize what those two are, and then any piece of data that would have come in during that time that got dropped by one party or the other just gets resent, right? There's, we don't sort of describe exactly how you store the data and how you identify what has been sent and what hasn't been sent. That's implemented on a application by application basis, but maybe you have sort of a warm cache where you keep really close track of things that might get, come and go over the second or over 10 seconds, and then maybe there's a colder one where we might keep sort of less granularity over things that might have been here a minute ago or 5 minutes ago, things like that. But this basically gives you the ability to pick up where you left off and identify all of the frames you missed in that small amount of time since you were last there. This is really, really key to a lot of the use cases we see RSocket using. Okay, right on time, great. So RSocket, as I said, is a bidirectional multiplexed message-based binary protocol, utilizes backpressure for its efficiency and predictability, provides primitives for the 4 common interaction models, flexibility almost anywhere, transport, language programming model, let us know what you want to use, and all of those other features we sort of ran through at the end. So with that, let me first thank you all for coming here and sitting in this giant room, and I'm happy to answer questions up here. Thank you.